Take
Hello,
the
my name is Sahas, and I'm going to be your coding coach for today. And um, I have Scott over here, and he's going to be actually the man in charge of today's lesson. Scott, would you like to introduce yourself?
Hi, thanks, Sahas. I'm Scott. I'm the computer vision lead for UCR UAS, and after we go over some of the practice problems from last session, we're going to be talking a little bit about the basics of computer vision and what we can use that for.
All right, cool. So yeah, in the Zoom chat we just sent in on the GitHub, we have the solutions to our last session's practice problems. So we're gonna just quickly go over them right now, just to make sure everyone knows how to do them. So Scott, could you please open up VS Code, and we will start with the practice problems. First things first, we want to test if print hello world works, which cool, it does. So that means everything is working so far, and we're going to move on to some of the problem sets. So we're going to comment out problem 0 because we don't want to see hello world again, and we'll uncomment out we'll just start with the first section of problem 1, and the solution, or what we need to do for this, so we need to set x to a value so that the output is false. So we have x equals, and we fill in the blank there, and then it'll print out x is greater than 5. And in order to make this statement false, we would need to just pick a number that is less than 5, and that will produce a false result. So if we pick the number 5 or 4 or any other number underneath that, it'll produce a false statement. Yeah, perfect. All right, so we'll just comment that out and then move on to the next problem set. And we want to make y a value such that y will, or that the print statement will produce a true statement. So this will use an or. So using Boolean algebra, since we have one false, and in order to produce a true, we need at least one true. So y should be set to true. And if we run this, we'll get true. So that means that worked. Now for the next one, it's a bit more challenging because there's more stuff going on, but when we take a look at the print statement, the goal is to make this true. So uh, first we'll try to deconstruct what's going on. We have a z and in parentheses, which means this will run first, not x or not y. So not x will reverse whatever x is storing, and not y will reverse whatever y is storing if it was a Boolean statement, and then we'll get the OR of both of them. So since it's an OR, we'll need at least one true. So what we can do is, if we make not x true, that means x would need to be false. So we'll put false for x, and then for y, it can be anything because we already have one true, so we'll just set that to true. And then that entire parentheses will produce a true statement, and then since we have an and statement with the z, we'll need to make sure that the z is also true, so that the entire statement will become true at the end. Yep. Any questions regarding problem 1? All right, if not, we'll move on to problem 2. And problem 2 will require us to use else statements, and we will be if else statements, my bad. So the context of the problem is we need to make essentially a legal drinking eligibility program where we have user input, and we need to see whether that user input is less than 21 or greater than 21. So first thing we'll go ahead and do is we'll create an if statement, and we'll check if user is greater than 20. And if user is greater than 20, so if they chose the number 21 or any number higher, that'll produce true, so that if statement will run, and then we'll just print you can drink. Else, so there's two ways we can do this. We can either do an else, because there's only two different conditions that can happen here, either above 21 or under 21. So we can either use an elif statement. So if we did elif and then user input is less than 20, or less than or equal to 20, then that will produce the true statement if they were under the legal drinking age. Or since there's only two options, we can just replace that with else, and then we'll do print you cannot drink. Now, before we run this program, does anyone see any flaws that might occur if we tried running this right now? Um, we can try giving it a run right now just to see if we get an error. So let's go ahead and run this code. What if user input isn't an int? Yeah, that is actually one of the problems. So when we use the when you type in something into input, that will always be stored as a string. So user input's actually going to be storing a string, and since you can't compare a string to an integer using the user input is greater than 20, we'll actually need to convert that into an integer. So we do casting. So to cast it, we'll just put int before input, and then parentheses, and then we just wrap everything in parentheses so that it'll get casted into an integer. And right now we're just assuming hopefully that they do just insert a number so that everything works. But if they were to enter a string in this case, we would get an error because you can't cast letters into an integer. So now if we run this, it should be able to work. Cool. Is there a way to detect if the input is a string and display? Yeah, so that's known as so that's a technique that we use in order to catch errors, like error catching. And just one technique we could use is I believe there is is integer or some a function that can be used to check whether something is an integer or is a string, and we can run an if statement on that. But there are other techniques we could use, um, but we can cover those during the office hours section. And then, yeah, so that's problem 2. So we'll move on to problem 3. This one's a bit more easier. So we'll uncomment our problem 3. And the concept for this is first we'll want to print out all the items in the list model trip. So to accomplish that, we'll need to use a for loop to do this. So we'll do the for I in. And then since we have a list, we can just type in the variable storing that list. And what that will do is I will be assigned all of the items one by one in multrip, and we can use that to print that out. So we can just do print I, and then this will print out all of the items one by one. Cool. And then the next section, oh yeah, we might want to comment this out.
My fault.
And then it's okay. And then for part 2 of the problem, what we'll is asking us to just print out the first 3 items. So to do that, we'll actually need to use the range function. So we'll do for I in range. And then since we want to print out just the first 3 items, we'll do in range from 0 to 3. And now that will mean I will run from 0 to 3, excluding 3, and it'll store starting at 0 and go all the way to the number 2. And then we will need to just use I as our as the way to talk about the index of multrip. So we'll reference that using the square brackets. And now it'll print out just the first 3 items. Yep. And yeah, that's the solution for problem 3. So problem 4 is a bit more fun because we get to kind of create a game in the process of coding it. So let's just uncomment all of this out. And the idea for this project is the computer is going to be creating will be storing a random number between 1 and 100 and storing that in variable target by using import random. So random is just a library that allows us to be able to produce a random number, and we use the randint function to do that. And once we have a random number selected, we'll be using this while true loop to create essentially a game loop that will ask the user to make a guess between 1 and 100 and store that as an integer in variable guess. And what we'll need to do next is we'll need to check if the guess is equivalent to the target. And if that's the case, they won the game and we break out of the loop. So we'll do if guess is equal to target, and we use double equal sign because we're comparing the two variables. Then we'll print out you guessed correctly, and we break outside of the loop. Otherwise, we want to give them hints to see how to get to the answer. So else, if the guess is, let's say, if the guess is less than the target, then we're going to tell them they guessed too low. And then else, which means if it's not, if they didn't guess the target and if they guess too low, then the only other solution is that they guess too high. And that's all we need to finish this code. So if we run this, we will be able to play the game. And Scott's going to be showing us a kind of um, a really quick way to do that. Since all the numbers are sorted, we can just eliminate half of all of the possible choices by picking the middle choice every single time. Yay. Good job, Scott.
Thanks, Ahas.
All right, and that's the solution to problem 4. So I'll comment that out and move on to problem 5. This one's relatively easy. All we're doing is we're creating a function to add and that'll take a number in and add 5 to that and return that out. So we'll do that by creating a function called uh I believe we called it add 5. So we use the keyword def to create the function, and it'll take an input as x. Um,
Oh,
I don't believe we can use the keyword input because that's already, I believe, restricted. So yeah, we'll use a variable x and we'll just return x plus 5. And that should be all for this program. So we'll type in a number and they'll just add 5 to that. All right. Now the last question is it's not too challenging because it doesn't really go over anything extremely complicated from the last session. But what we're doing is we're adding and fixing up the Fibonacci sequence so that it would print out the solution. So right now, Scott already has a bit of the solution, I believe, already written up. So we'll just delete that and start from scratch. So just, yeah, it's from line 61 mhm, and 162 as well. Okay, so the Fibonacci sequence, it starts with the number 1, and then we get and it starts with two ones for the beginning two terms, which is denoted by n1 and n2, and then we have current term being tracked using by setting that equal to 0, and then we have temp variable set to 0 as well. And what's going to happen is a bit lower on line 165, we're going to get input from the user and we're going to ask them how many terms we want printed out in the Fibonacci sequence. That gets stored in n, and then we will just return that into print fib n, and then that goes into our function. The first thing we do is we check if n is less than or equal to 0. If that's the case, we'll ask them to just enter a positive number, and then we return out. Otherwise, we're going to start to print out the Fibonacci sequence. So we're going to do, one more thing we actually that I think got removed maybe. Oh, no, never mind. We're good. So else we'll print out the Fibonacci sequences up to, and then we'll have a while loop. You might want to tab in the while loop inside the else statement, Scott.
oh, yep.
So now this is the place that we're adding the code. So we're going to be printing out n1 as the current term. So to get the next term, we'll first use the temp variable and set that equal to n1 plus n2. And then we're going to update n1 so that it's storing n2's variable. And then we update n2 so that it's storing temp. And then we increment the current temp variable by 1. And we can do current temp equals current temp plus 1, but a shortcut to that is just doing plus equals 1. So now if we run this code, it should give us the Fibonacci sequence. Yeah, so that's the Fibonacci sequence program. Any questions regarding the homework? Slightly unrelated, but what color theme are we using? Scott, what theme are we using?
Monokai Pro, it's great. Not sponsored. Monokai hit me up.
All right. Well,
Yeah, no
that was
problem.
all of the solutions for this set of homework, and now we can just move on to the actual lesson plan. Scott, I'll hand it over to you.
All right, thanks, Ahas. So yeah, now that we finished going over the homework from last session, today we're going to go over a little bit less of a technical uh, workshop today, and we're going to be talking about something that I think is pretty cool that you can do with Python, which is computer vision. So, being the computer vision lead, I've been practicing a little bit with computer vision to say the least, and I think this would be really interesting to show you all. So, feel free to follow along if you would like, but if not, then just sit back and take in the math. All right. So, first of all, what is computer vision? Because I know that when I first started computer vision, I didn't really know what it meant. Like, it's just cameras, right? But um, it's a little bit more complicated than that, in that we have an image from a camera, and then we have a computer that doesn't really have a brain like us, but we have to figure out how we can tell the computer what's going on in the picture. So we can take images from a foreground and a background. So taking out this parrot, we can tell if there's a bicycle, a dog, and a car in a picture. We can tell that this is indeed Obama with two eyes. So there's a bunch of different uses for computer vision, and these are just some of them that are a little bit more simple. So the history of computer vision. So despite what it sounds like, it's actually a really old technology, albeit a lot better than it used to be. So um, research actually started, or the idea of computer vision started around the same time that modern computers started to be developed. So people were wondering, hey, can we create a computer or an artificial intelligence that's simulating the visual system of a human, and they were trying to do that for well up until now, and they're getting fairly confident with this. So um, starting around the 1970s, they started to find out how we can see whether there's edges on an image, as well as seeing if we can with hard coding values, if we can find whether certain images have different objects. So we could write very exact values to say, okay, if I put in a picture of a bicycle, it will tell me if it's a bicycle or not. If I put in a picture of a camera, it'll tell me if it's a camera or not. So later on, toward the 1990s, we were people or engineers were trying to reconstruct 3D scenes from sets of images. So think of this as a precursor to panoramic images, as well as using computer vision to work a little bit backwards in the work pipeline and calibrate cameras a lot more efficiently and more precisely. Come the 2000s, we have panoramic image stitching. So if you notice, um, a lot of panoramas were coming around the mid 2000s because this is a pretty new technology, and being quite honest, it's pretty cool. We have a lot of computation optimization. So before, not only because of physical constraints, the algorithms that people used were um, a lot less efficient than they are now. And there's also the SIFT algorithm, which is an object detection algorithm that's really, really efficient and really effective. And toward the 2010s and the present, I'm sure you've all heard of deep learning, which is quite a scary subject to begin with, but that's a really advanced version of computer vision, which uses more machine learning and artificial intelligence, is which looks to be the future of this field, as well as the YOLO algorithm, which is not you only live once, but it's you only look once. Um, why they named that? It's computer science people, so of course. But basically, instead of the computer doing a bunch of calculations on one image, they just go through it one time without doing overlaps. So that makes computation a lot more efficient. Okay, so moving on to the actual content, the first thing that we need to talk about is how does a computer see the images? Well, with our eyes, there aren't really pixels, right? We just kind of take in light into our retinas. Well, when we take pictures with a camera, the sensors take in light at certain spots and we write that into a grid basically. So in modern computers, images are stored as arrays of pixels. So think of a, a really big grid with certain number of layers, and each cell of that grid is a pixel. And the each layer can either be red, green, blue, which is really common in LCD screens, I don't know, gaming accessories, computers, and there's also HSV, which is hue, saturation, and value. So with hue, saturation, value, if you're accustomed to drawing or photography, this might be familiar, but the hue changes what color or what part of the visual light spectrum a color is part of. The saturation, if you can see on the bottom diagram, is how gray or how vibrant a color is. And the value is just how bright it is. So from black to the brightest color that you can get. If you're talking about black and white images, then the depth is only one. So it goes from 0 to 255, 0 being black and 255 to being white. Okay. Any questions on that so far? Okay, cool. So again, if you have any questions, go ahead and ask in the chat. I will be checking it as I go through. But let's move on. So here's an example of what an image looks like. So here's a really blurred photo of Abraham Lincoln. So on the left side, you can see the original image. And then toward the middle, you can see each pixel is paired up with a number. And it might be a little bit blurry, but if you can see the numbers, you should notice that the really dark squares are paired with really low numbers. So the parts of his beard that are black are 0, 0, 1, 12, you know, and then his forehead's pretty bright. So it's in the 250s, right? And if we take out the visualization and we just have the numbers, well, humans can't really see that, but that's really important to computers. Yes, forehead. Okay, so the really important part of computer vision is image processing because while it is really easy to tell what parts of images are important from a human's perspective, sometimes computers um, don't really know what they need to pull out of an image or what they need to focus on. So what we do is we can process it. So the first step is image smoothing. So photos can have noise in them. So that's basically unwanted details. So that can be textures that are too fine for what we're using computer vision for. It could be bumps in the road. It can be specks of dirt on someone's shirt, right? Like the computer isn't going to really care about that at all. So what it does is it runs through the entire photo, taking uh, an average of every pixel basically. So if I take out my wonderful picture here, can everyone see that?
Yeah.
Awesome. All right, so if we take our wonderful picture here, and we have our little kernel here. This is called a kernel, so that's today's keyword. So we take our kernel, and we take an average. We take a weighted average over the entire image. So we take this. So these lower right pixels have a black line in it, and everything else has sky. Well, presumably sky. Where's the trombone? Out of frame. I'm taking a break. um, so it takes an average and it spits it out into a new image. So this image stays intact so that we can make calculations off of it. And then we store the calculated average of that pixel into a new image. And we do that for every single image in the original photo. So we move one, we move another, and we keep on doing that until the edge of the row, and then we move down by one row and restart. And we just basically go through that entire image until we get to the end. And our result is a really um, a really blurred image. Oops, that red is not going away. A really blurred image that is it still shows the main features. So in this case, the person in the middle. However, if you look at the sides, our little trees from before, they're not there anymore. They're just smudges, so the computer's not really going to pick it up. And the same thing with these little tufts of grass down here. So these little tufts of grass, they're getting smoothed out over the image as well. So the main feature in this image is a person, right? And that's really important because we don't want to waste computing time on things that we don't really want. So next thing to do is we can find edges. So what it does is it looks at certain pixels and sees if the pixels around it are different from each other. So if you think about the edge of this cat's skin, or fur, I guess would be a better word for it. If we look at the edge of this cat's fur, we know that, yeah, exactly. This is Snapchat filters, right? So a lot of social media filters actually use computer vision techniques in order to make your, I don't know, put your sunglasses on your face, or make the whole screen like in a hue of purple or whatever. So for edge detection, we're going to be looking. So let's say I'm looking at the edge of this cat's fur. The way that the computer knows that this is an edge is that the white on the left is a lot different from the green on the right. And the same thing for the top of the cat's head. We have the black of the cat's fur is different from the brown of the mountain in the background. And it does that over the entire image, as you can see in this GIF over here. And anything that's edgy enough, I guess edgy, if it counts enough as an edge, I guess would be a better way to say it, then the pixel turns white. And if not, then it turns black. So that's how we have this output here, right? And mathematically, how does that work? Well, we have our we have our really simplified example here. So let's say we have a grayscale image that's exactly 3 pixels wide. So this is a really small image. And we have our kernel just like before. Let's make this a black pen. So we have our kernel from before, and we're going to cut it down to 3 wide. And we're going to have our values of -1, 0, and 1. And these kernels, as long as one side is the opposite sign of the other side, then that kernel is good for edge detection. So what we do is we multiply each corresponding value with the value in the kernel. So 0 gets multiplied by -1, 100 gets multiplied by 0, and 255 gets multiplied by 1, right? So we have 0, right? 0 times -1 is 0. 100 times 0 is 0. 255 times 1 is not 1, 255. And what we do is we take an absolute value of all of them added together. So of course we get 255. And this is kind of our edge value. So what we can do is we can set up a lower limit. So let's say anything that has an edge score over, let's say 150, right? If our edge score is over 150, then that pixel counts as an edge. So this pixel would be the same as the pixel on the edge of the cat's fur. So one side is a lot different from the other. Yeah, so again, so this is the threshold. So this is the lower limit of what the edge is. So anything under that does not count as a strong enough edge. And that means it's not going to be written as an edge. And although the positive and negatives kind of line up here, we can also do it with an opposite looking edge. So we have, unlike the above picture, we have a lighter hue, or sorry, not a lighter hue, a lighter value on the left and a lower value on the right. So we have let's say we have the same kernel, -1, 0, and 1, and we multiply each one in. So we have -175 plus 0 plus 0, right? And then we take an absolute value, and that just comes out to 175. And 175 is greater than 150, so this counts as an edge. Now, if I had, for example, 20, 0, 20, well, it would be -20 plus 0 plus 20, and then you take the absolute value. Well, this is just the absolute value of 0, and that's 0. So this does not count as an edge. So if you think about it, if the two sides of a pixel are the same, then that doesn't really mean it's an edge. That just means it's part of the same color. And one last note is the middle is always 0. So if you think about it, we don't really care about what the edge pixel is actually holding. We only care about its neighbors and whether they're different enough from each other to constitute an edge. So we do that in both the x and the y direction so that we can see whether there are vertical edges or horizontal edges. If there's any questions about that, I can start taking them now. Otherwise, we can move on to the next step of the image processing pipeline. All right, so there's no question. Oh, are the kernel values always -1, 0, and 1? Good question. So a lot of the time, I'll make a new layer. A lot of the time, the most common kernels, they actually use two different kernels. One's for vertical and one's for horizontal edges. So for horizontal edges, the more common one is using -1, -2, -1, 0, 0, 0, and then 1, 2, 1. So with this, that means the middle section right here has a little bit more value to it, because if we have an edge, we don't really we do care about the diagonals, but the more important things are the pixels right adjacent to it, right? So yeah, that's a horizontal direction kernel, and then for a vertical edge kernel, we have the exact same thing but turned sideways. So we have -1, -2, -1, 1, 2, 1, right? And then, so a lot of people, they run both of these and they look for the score. And if both of the scores, so they run both of these kernels separately on the same image. Let's say this was 152 and this one was 175. And our threshold, our minimum value, is 150. Then, well, both of these pass the test of whether it's greater than 150. So that means it is an edge. So yeah, that was a good question. This is a little bit more of the technical side of how they do edge detection, but yeah, so this is how people around the 1970s were actually doing this. So if you think all the way 50 years back, people were doing this kind of stuff with images, which I think is pretty cool. Moving on. So if you noticed from our last slide, our cat looks kind of stringy, to say the least. So we need to make those edges a little bit thicker for our computer to understand what's going on a little bit better. And how we do that is through morphological transformations. So how we do that is we have two different functions called erosion and dilation. So if you think about the word erosion, that means the rock, something like a rock gets worn down over time and it gets smaller, and only the outside gets eliminated. And the exact same thing happens here. So how erosion works is we look at every pixel in the bitmap, and a bitmap is just like an image, except it's just 1 or 0. So 1 is perfectly white, and then 0 is perfectly black. And when we erode, what we do is we look through every pixel and we see if that pixel is surrounded by only white pixels. And if it's only surrounded by white pixels, then it stays white. So that means anything on the edge is touching a black pixel, and thus it gets eliminated and turns to a 0. And anything that's in the middle, well, the middle is surrounded by white. So that's why the middle section is of this letter J is conserved. And the exact opposite happens with dilation. If you think about dilating your pupils, so um, so when we perform dilation, we see are any black pixels touching white pixels, and if the black pixels are touching white, then we um, turn that pixel white. So that means anything in the neighborhood of the white pixels turns white. And I think here's a good now is a good reminder that we don't want to actively edit the original image that we're calculating, because if we say that okay, none of these are touching black pixels, and then um, if we continue through that, it's basically going to turn the image black. So we don't want that in computer vision, in a computer vision standpoint. So what we do is we do the calculations on this image, and on the side we have another image that we're filling in, right? So that's our basics of morphological transformations, and here's one use of it. So here we have a letter J, which has a bunch of white spots around it. And this is, well, I guess it looks pretty, but we don't want that if we're trying to, for example, read what letter is written here. So we want to get rid of these white dots, right? And how we do that is we can do an erosion. So if you remember, anything that's touching a black pixel is eliminated in erosion. So these dots are a little bit too small to survive, for a lack of a better term, the erosion. So that means because the entirety of these white dots are touching black dots, then they're eliminated. And then we get rid of the outsides of that J because they are touching the black pixels. And then we have a skinny J. And this doesn't look great. It's not true to what the original image is. So what we can do to fill that back up is we can perform a dilation. And because we just cut things down, we can fill things back up with the edges. So we can make these a little thicker. And we can do that again by saying, okay, which black pixels are touching white pixels? Well, it's everything around the outline of the J. So we can turn the outline white and we have a thicker J here. Do you have any questions on that for now? Okay, cool. So moving on to contours. So we have our bitmap, right? So we have our filled in outline. In this case, it's a hand. And well, we need to find where that outline is exactly. So we can do something called finding contours, which is basically a curve of white pixels that are connected to each other. As you can see with the yellow outline on the slides, we have the yellow outline following the edge of this white bit mask, right? And if you think about it, if this bit mask was all craggly and there was a bunch of dots around everywhere, the contour finding would get kind of confused. And well, obviously that's not a good thing. So we want to make things as clear as possible for our object detection. So now that we have that, how does this all come together? Well, here's an example of what UCR UAS actually does in their computer vision team. So we are tasked with finding targets on the ground um, with a camera that's being hung up from a UAV or a plane. So first, let's say we take this picture, and I've cropped it a little bit so that we have more room on the screen. So the first thing that we do is we run it through a blurring, and a Gaussian blur is just a certain way to weigh the blurring. So instead of just doing an average, there's different values that you put in for the average. So here we get rid of some of the noise in that we are eliminating some of the darker spots of grass and the gravel on the bottom right, because, well, we don't really care about those. We only care about the really prominent and vibrant pictures on the ground, which is, in this case, this blue triangle. So next we use edge detection. So we see that in this case, the blue is really different from the green, and the white is really different from the blue. So now when we run edge detection, the not the red, white, and blue, the green, white, and blue are all separated from each other through edges. And we don't really care at this point what letter is on this target. So what we do is we run a really big dilation around the bitmap. So here we have, actually we do an erosion followed by dilation. So if you see these dots here, well, they get eliminated, and then the existing lines get filled in, as well as some of these blobs at the corners. So we'll deal with those in a bit. So when we deal with when we perform the contour finding, we are looking at the continuous white pixels again. So in this case, we have the white corner at the top right, and then we have this little blob on the right, and then another blob on the bottom left, bottom center. And these are extra, but that's okay because what we can do is we have our bounding rectangle. So what we can do is we can look through every single contour and we can see whether they're big enough. So any contours that are smaller than a certain pixel area, we don't really care about because the targets can't be that small. So again, this is really an example of how specific computer vision can be, because let's say we were looking for like ants from a video, then maybe those smaller contours would be useful. But in this case, we only care about the bigger ones. And then we can use our computer vision library to draw a rectangle around it. And from that rectangle, we can crop the entire image out. Right. And okay, so that was an avalanche of information. So how are we doing? Does this kind of make sense conceptually yet? I haven't shown any code, but I will in just a bit. Okay, cool. So no questions now, but we remember, if we have any questions, then go ahead and ask. This is really for you guys to learn about some of the more obscure things that you can do with computers, because uh, this isn't always the first thing that you think of when you think Python. Okay,
Yeah,
so
just real quick about that object detection. So it only really works if the background is kind of the same, right? If, for
yeah,
example, you
exactly.
put that target a place with a lot of rocks, isn't probably not
Hmm.
gonna work.
Yeah,
Okay.
so um, that's that's a really good point. So if there were, I don't know, if there was a really big boulder on the side, then that might be taken as another object, and you, that would be another problem that the computer vision team would have to check. So how can we check if that rock is a target or not? Well, we can see, is it round enough to be a circle? Is it sharp enough to be any other shape? And that's a whole different thing that we're not going to have time to go over this meeting. But um, the basics of it is we try our best to get rid of those features that we don't care about, but eventually some things do come up, and we end up cutting out whatever the computer thinks is correct. So in this case, if there were a boulder, then the computer would cut out both the boulder and the target. Yeah, good question. So moving on, we can also do computer vision in real time because, as we were talking about before, computer vision algorithms have gotten really, really uh, efficient compared to what they used to be. So we can actually take live video feed from a webcam and run some algorithms on it. So if I pull up my Python, so I'll just run through the code really quick. So here we have our import statements. So this is similar to how we imported random for our homework earlier. So we import computer vision. So it's called CV2 because it's version 2. And then we have NumPy, which is a library that's really important because of how simple Python is, it's not super efficient in terms of doing math. So what people have done is they write certain math libraries in a different language, usually C or C++, and then they just translate the functions into Python, and it's called a wrapper. So we type in Python, but under the hood, the computer is actually using C++ code. Okay, so now our kernel is our kernel for our morphological transformation that we're setting up right now so we can use it later. Again, our keyword today is kernel for your extra credit. And then we have cap equals cv2.video capture. So capture or cap is going to be taking in our video. Yes, Python is basically C++ at the skin. Don't tell anyone. It's just easier. Okay, and if we have a continuous program running, well, what better method than to use a while loop, right? We want to run code until we don't want to anymore, and we can use a break statement to do that. So now we do ret, image equals cap.read. So we cap.read actually returns two different values. So it returns into return and image. And ret we're not using right now, but we need to have it there so Python doesn't yell at us for not putting it away. But yeah, so our image here is basically whatever's coming out from my webcam. And the next few steps are our processing functions that we were talking about before. So Gaussian blur is our image smoothing algorithm. So this is built into CV2, which is really nice. CV2 is, by the way, an open source computer vision library called OpenCV, developed by Microsoft, I believe. So this is really useful, so we don't have to reinvent the wheel. So we take an image, we smooth it, we store it into process. Actually, this should be process. Okay. So now we store into process canny. So canny is a type of edge detection, which works very similar to what we were talking about before, but it's a little bit more efficient. So we have our input image and our thresholds. And then we use a dilation to try to get the edges to be a little thicker. And then here we have contours and hierarchy. Same thing with hierarchy between return and hierarchy. We're not going to be using it, but it is useful for very, very specific things. So we store our contours, which is again the curves that we can see on the image, by using the find contours function. And these return tree and chain approx simple are both telling CV2 which algorithms to use to calculate the curves. And the next thing that we're doing is we're going to loop through the entire contour list. So this this variable contours stores a bunch of contours. So we look at every single contour within that list. We check if it's a certain area. So in this case, we say if it's less than 500 pixels squared, or if it's greater than 1000 square pixels, then we just skip it. It's not worth our time. If it's inside of our bounds, then it is worth our time. So what we do is our we find our coordinates for the rectangle, and then we draw a rectangle around here. So it's going to be 0, 255, 0, which is green. And in here we use cv2.im show, and that lets us show our original image, which is stored in img, and our fully processed image, which is stored in process. And at the end of the while loop, we use cv2.wait key, which is, oops, I did not mean to do that, which is just telling the program to wait for 1 millisecond. And then we can also check if we press the Q key. So basically, if I press Q, then the whole program stops. And if we do, then we break and the rest of the code does not happen. So if we run that, just wait a little bit for it to start up. Hello, Python. Actually, I might have to turn off my video for Zoom. Here it is. So if you can see me on the main screen now, there's a bunch of, actually, the letters on my shirt are actually counted as objects. So if you look on the right side, you can see that the dots are kind of like artifacts of edges that it found. But because the text of Riverside is kind of spotty, it's not showing exactly as perfect lines. So that's something that could be improved on for image processing. However, something like, let's see, oh, I guess oh, so if you look at the knuckles on my hand, apparently on the right side, the little line on the edge of my finger counts as enough of a shape. So can it detect my trombone? Probably if I tried hard enough, but we're close to being out of time for that. So I hope, I'll just keep this on. So um, as you can see, this is running pretty well actually. I think it's running at 30 FPS. But yeah, so this is the really basic parts of computer vision. And yeah, that's basically everything that I had for today. And just a reminder that our kernel, or our word of the day is kernel. And at the end, to end this off, we have some words from our business team.
Okay, hi guys. My name's Trang. I am operations and outreach at the business team at UCR UAS, and also the face behind our technician for all of our events. You guys probably know about us already. We build planes. We host educational events like this, and recently we have chosen a flight team for our composition. So that's pretty exciting. We'll keep you updated if you guys sign into our newsletter. Um, Continuing with updates.
Oops.
Um,
Oh, what happened? Oh, yes. There you go.
yes,
Sorry about that.
it's okay. So yeah, we are actually still hiring. We need one experienced mechanical engineer to build our competition plane, and our business team is still looking. We're still open for outreach, marketing, and finance specialists. Um, please go to our website and apply before the end of this week. Yeah, and that's it from us. If you enjoyed this workshop and you have some spare change or something, feel free to donate to our Venmo or GoFundMe and support our operations. Thank you for being here, and don't forget to sign in. Our keyword is kernel.
All right. Thank you, Trang. Okay. And with that, I think that is the end of our workshop. So I hope you followed along with the homework review and I hope you thought that the computer vision was pretty interesting. And again, we're gonna have office hours from 6 to 7. If you have any questions about computer vision or Python in general, or anything that you didn't get from the review for our session 2 homework, then we're going to be around for about an hour. So feel free to stay. But I hope everyone has a good week and survives midterms because online school is rough. Um, so do your best, don't die. Um, yeah, that's about it. Anything else, Sahas?
Nothing from me, Scott. But
Awesome.
thanks for everyone for coming.
Yes, and follow us on Instagram and stuff. Shameless plug.